The question that haunts every astronomer tracking 3I Atlas is fundamentally simple, yet cosmically profound. What are we actually looking at? The morphological transformation, captured by the Nordic Optical Telescope, is not merely an aesthetic curiosity. It is a physical signature, a message written in dust and light that speaks to the object's internal composition and the forces acting upon it. An antitail, by its very nature, is a structure created when larger dust particles are pushed outward by solar radiation pressure but then fall back along the object's orbital path, creating an apparent spike that points sunward from our earthly vantage point. It is an optical illusion of sorts, a trick of perspective and physics. The transition to a conventional tail, however, suggests a fundamental change in the type or quantity of material being expelled. A tail is the classic signature of cometary activity, volatile ices sublimating under solar heating, releasing gas and smaller dust particles that are then swept away from the sun by solar wind and radiation pressure. The tail is the exhaust plume of a comet in distress, vaporizing under the brutal assault of solar energy. For 3I Atlas, this transition is happening precisely as it approaches perihelion, the moment of maximum solar exposure and maximum stress. The timing is perfect for natural cometary behavior, yet the context is anything but ordinary. The object's record-breaking carbon dioxide levels mean it is carrying an enormous quantity of volatile material, far more than typical comets born in our own Oort cloud or Kuiper belt. Carbon dioxide sublimates at a lower temperature than water ice, meaning 3I Atlas could have been actively outgassing long before it reached the inner solar system, potentially explaining some of its non-gravitational acceleration observed months ago. Non-gravitational acceleration is the technical term for a phenomenon that has become central to the entire debate surrounding interstellar objects. When an object in space accelerates or decelerates in ways not fully explained by the gravitational pull of the sun and planets, scientists must account for other forces. For comets, this typically means the rocket effect. Jets of gas erupting from the surface as ice sublimates, creating tiny thrust forces that alter the object's trajectory. The first interstellar object, 1I Oumuamua, famously exhibited non-gravitational acceleration without any visible cometary tail or outgassing, a paradox that led Dr. Loeb to propose it might be a light sail, a piece of alien technology propelled by solar radiation. 3I Atlas does show signs of outgassing, making it more conventionally comet-like than Oumuamua, yet its chemical signature remains deeply anomalous. The detection of nickel in its coma, the cloud of gas and dust surrounding the nucleus, is not itself unusual. Many comets contain trace metals. What is unusual? What prompted scientists to describe the finding as contradicting chemical expectations is the apparent absence of iron in comparable quantities. In the standard model of stellar and planetary formation, nickel and iron are forged together in the cores of massive stars and expelled together in supernova explosions. They are cosmic siblings, born in the same nuclear furnace, and they condense together in the protoplanetary disks that form around young stars. A comet with abundant nickel but little detectable iron is a chemical orphan, a composition that does not fit the expected recipe for objects formed in stellar systems like our own. This raises a tantalizing, uncomfortable possibility. Did 3I Atlas form in a stellar environment fundamentally different from our sun's, perhaps around a star with an unusual elemental abundance, or in the aftermath of a rare type of stellar explosion? Or, as Dr. Loeb continues to suggest, could the anomalous composition be a clue to an artificial origin, a manufactured object with a deliberately unusual elemental makeup? The stakes of this question extend far beyond 3I Atlas itself. If this object is natural but formed under exotic conditions, it tells us that the interstellar medium, the space between stars, is far more diverse and strange than our models predict. If it is artificial, it represents the first tangible evidence of extraterrestrial technology, a discovery that would redefine humanity's place in the universe. The ambiguity is maddening, scientifically electrifying, and philosophically profound. Every new observation either deepens the mystery or shifts the balance of probabilities, but never fully resolves the central question. The Nordic Optical Telescope images, analyzed and published by Dr. Loeb's team just hours ago, provide the most recent data point in this unfolding saga. The images show the dust distribution around the nucleus changing over time, the glow shifting from a sunward spike to an anti-sunward plume. This is exactly what one would expect from a natural comet, ramping up its activity as solar heating intensifies. Yet the object's current location, deep in the dayside sky and nearly invisible to most instruments, means that these images from the Canary Islands may be among the last clear observations we can obtain before perihelion. The Sun, our source of light and life, has become the object's cloak, hiding it from our most powerful telescopes at the very moment when its behavior is most critical to understand. NASA and ESA spacecraft, positioned throughout the inner solar system, have been attempting to track 3I Atlas using both optical and infrared instruments. Mars Express, ExoMars Trace Gas Orbiter, and Mars Reconnaissance Orbiter have all been tasked with observing the object, leveraging their positions in Martian orbit to gain different vantage points. These spacecraft, designed to study Mars, are now makeshift sentinels of the interstellar visitor, their instruments repurposed for an observational campaign that was never part of their original mission. The data they collect is invaluable, yet Dr. Loeb's recent statements suggest frustration with the pace and transparency of data release. His allegation that NASA may not be fully transparent about the data it possesses is a serious charge, one that touches on the broader issues of scientific openness and public access to taxpayer-funded space research. In the age of instant communication and global scientific collaboration, the withholding or delayed release of data on an object as extraordinary as 3I Atlas is seen by some as unacceptable, a barrier to the rapid, open scientific process that such a discovery demands. Others argue that data must be carefully calibrated, verified, and contextualized before public release to avoid spreading misinformation or premature conclusions. The tension between these perspectives is not unique to 3I Atlas, but the object's potential significance amplifies every disagreement into a matter of profound public interest. What if the withheld data contains the definitive proof of the object's nature? What if the images or spectra already in NASA's possession show something so anomalous, so unprecedented, that their release is being delayed for reasons beyond standard scientific caution? These are the questions fueling the current controversy, questions that will likely remain unanswered until the perihelion passage is complete and all data is finally made available for independent analysis. The scientific method, at its core, relies on reproducibility, transparency, and the free exchange of information. When an object like 3I Atlas appears, an object that challenges our fundamental understanding of what is possible in the cosmos, the stakes for maintaining those principles become existential. The morphological change documented in the Nordic Optical Telescope images is a physical fact, a transformation captured in pixels and analyzed through rigorous photometric techniques. The interpretation of that fact, however, remains contested. Is the shift from anti-tail to tail merely the predictable result of increased solar heating and enhanced sublimation of carbon dioxide ice? Or is it a sign of something more complex, a change in the object's internal structure or activity level that cannot be fully explained by conventional cometary physics? The answer lies in the details: the exact timing of the transformation, the spectrum of light emitted by the gases in the tail, the velocity and distribution of the dust particles, and the correlation between the tail's appearance and the object's trajectory. Each of these parameters can be measured, modeled, and compared to theoretical predictions. The work is painstaking, requiring the combined efforts of observational astronomers, spectroscopists, dynamicists, and computational modelers. It is science at its most collaborative and most demanding, a global effort to extract meaning from a fleeting cosmic event. The question of transparency in space science is not new, but the arrival of interstellar objects has brought it into sharp relief. When 1I Oumuamua was discovered in 2017, it spent only a few weeks within range of Earth's telescopes before speeding back out into the interstellar void. The brevity of that observational window meant that every hour of telescope time, every spectrum, every image was precious beyond measure. Scientists scrambled to observe it with every available instrument, from ground-based optical telescopes to space-based infrared observatories. Yet even with that intensive effort, Oumuamua departed, leaving more questions than answers. Its shape, inferred from its unusual light curve, suggested an extremely elongated or disc-like structure, unlike any asteroid or comet previously observed. Its non-gravitational acceleration, detected through precise astrometric measurements, implied outgassing, yet no cometary tail or coma was ever detected. The combination of these anomalies led Dr. Loeb and his colleague Dr. Shmuel Bialy to publish a paper suggesting that Oumuamua might be a light sail, a thin reflective structure propelled by solar radiation, possibly of artificial origin. The suggestion was met with intense skepticism from much of the astronomical community, yet no fully satisfactory natural explanation has emerged. The object is now far beyond the reach of any telescope, forever beyond further study, its true nature permanently unknowable. 3I Atlas presents a similar challenge, but with one crucial difference: we had more warning. Discovered months before its perihelion passage, it has been observable for a longer period, allowing for more extensive study. Yet, the same fundamental problem remains. It is a visitor, a transient, and once it departs, it will never return. The opportunity to study it is finite, measured in weeks and days, and now, as it plunges toward the sun, measured in hours. The pressure on astronomers is immense, the scientific stakes incalculable. Every observation must count. Every data point must be carefully preserved and analyzed. The allegation of data withholding, whether accurate or not, reflects the anxiety of a scientific community acutely aware that the window of opportunity is closing. The carbon dioxide levels detected in 3I Atlas are not merely high, they are record-breaking for any object observed in our solar system. Carbon dioxide is a common component of comets, but typically in much smaller quantities than water ice. In 3I Atlas, the ratio is reversed, or at least significantly skewed, suggesting formation in a colder, more carbon-rich environment than the regions where our own comets formed. The outer reaches of protoplanetary disks, beyond the so-called snow line where water ice can condense, are rich in volatile ices, including carbon dioxide, methane, and ammonia. If 3I Atlas formed in the outer regions of its home stellar system, perhaps in a disk around a star cooler than our Sun, it might naturally have incorporated more carbon dioxide relative to water. Alternatively, if it formed in the aftermath of a stellar collision or in the ejecta of a supernova, its composition might reflect the unusual chemistry of those violent events. Each scenario is physically plausible, yet each raises further questions. The detection of nickel without corresponding iron remains the most chemically puzzling aspect. Spectroscopic observations of the coma, the tenuous atmosphere of gas and dust surrounding the nucleus, revealed emission lines characteristic of nickel atoms, released from the nucleus as surface ices sublimate and expose underlying rocky material. In a typical comet, such metal emissions would include iron as well, usually in greater abundance than nickel, reflecting the cosmic abundance of these elements. The apparent absence or significant depletion of iron in 3I Atlas suggests either an unusual parent body composition or some process that preferentially removed or sequestered iron. One hypothesis is that the parent body, the larger object from which 3I Atlas might have been broken off, had undergone differentiation, a process where a planetary body separates into layers of different composition due to melting and gravitational settling. In a differentiated body, heavy metals like iron sink to the core, while lighter materials rise to the surface. If 3I Atlas is a fragment from the mantle layer of such a body, it might be depleted in iron relative to nickel, though this explanation requires a complex formation history involving planetary-scale processes. Another hypothesis is that the object formed in a stellar environment with an unusual elemental abundance, perhaps a star that had itself formed from gas enriched in nickel from a previous generation of supernovae. Stellar nucleosynthesis, the process by which stars forge heavy elements, is not uniform. Different types of supernovae produce different ratios of elements. A type Ia supernova, caused by the explosion of a white dwarf star, produces large quantities of iron peak elements, including nickel. But the exact ratios depend on the details of the explosion. If 3I Atlas formed from material enriched by such an event, its composition might reflect that unusual heritage. These are speculative explanations, yet they are grounded in known astrophysical processes. The challenge is that we cannot test them directly. We cannot visit 3I Atlas, cannot land a probe on its surface, cannot return a sample to Earth for laboratory analysis. All we have are the photons, the light emitted or reflected by the object, captured by our telescopes and analyzed through spectroscopy. It is detective work at the most fundamental level, inferring the nature of distant matter from the fingerprints it leaves in the electromagnetic spectrum. Dr. Loeb's persistent advocacy for the artificial origin hypothesis is grounded in a different kind of reasoning, one based on Bayesian probability and the principle that extraordinary claims require extraordinary evidence. His argument, simplified, is that given the vast number of stars in the galaxy and the potential for advanced civilizations to arise around some of them, the detection of interstellar artifacts should not be dismissed out of hand. If such artifacts exist, they would likely exhibit anomalous properties, characteristics that do not fit neatly into our existing categories of natural objects. Oumuamua's elongated shape, high reflectivity, and non-gravitational acceleration without visible outgassing are, in this view, exactly the kinds of anomalies one might expect from a technological object. 3I Atlas, with its chemical oddities and rapid morphological changes, fits a similar pattern. The counterargument from the majority of the astronomical community is equally straightforward. Interstellar space is vast. The number of natural objects ejected from other stellar systems is likely enormous. And the diversity of planetary formation environments means we should expect to see unusual compositions and behaviors. Every anomaly does not require an exotic explanation. Nature is more creative than our models anticipate. The debate is fundamentally about priors, about the probability one assigns to the existence of extraterrestrial technology before examining the evidence. Those with low priors require overwhelming proof. Those with higher priors see suggestive hints in every anomaly. The scientific method is designed to navigate this tension, to weight evidence objectively and update beliefs accordingly. Yet the process is complicated by the fleeting nature of the observations and the incompleteness of the data. As 3I Atlas approaches perihelion, the solar heating is intensifying exponentially. At perihelion, the object will be approximately 0.64 astronomical units from the Sun, well within the orbit of Venus, exposed to solar irradiance more than twice as intense as Earth receives. For an object rich in volatile carbon dioxide, this is a crucible. The surface temperature will rise rapidly, potentially exceeding the sublimation point of all surface ices, releasing vast quantities of gas and creating a dense, bright coma. If the object has a rocky or metallic core, that core may become exposed as the overlying ice vaporizes. This is the moment of maximum activity, maximum brightness, and paradoxically, minimum visibility, as the object is positioned almost directly between Earth and the Sun, lost in the solar glare. The images from the Nordic Optical Telescope, captured before the object became completely invisible, may represent our last clear look at its structure. The tail, now pointing away from the Sun, will grow longer and brighter over the coming days, potentially becoming visible to specialized coronagraphs, instruments designed to block the Sun's direct light and observe the faint corona and nearby objects. NASA's SOHO spacecraft and the Stereo mission, both equipped with coronagraphs, are being tasked to search for 3I Atlas during its perihelion passage. These observations are technically challenging, requiring precise pointing and careful subtraction of background light, but they represent our best hope for tracking the object through its closest approach. If the tail becomes sufficiently bright and extensive, it may be detectable even against the overwhelming glare of the Sun, providing crucial data on the composition and quantity of material being expelled. The European Space Agency's Solar Orbiter, currently in a highly elliptical orbit around the Sun, may also have a unique vantage point for observing 3I Atlas, depending on the relative positions of the spacecraft and the comet during perihelion. The dynamics of the tail itself are governed by complex interactions between solar radiation pressure, solar wind, and the intrinsic properties of the dust and gas particles. Larger dust particles, less affected by radiation pressure, form a curved dust tail that follows the object's orbital path. Smaller particles and ionized gas molecules, strongly affected by radiation pressure and magnetic fields, form a straight ion tail pointing directly away from the Sunday. The morphology of these tails, their brightness, color, and evolution over time, provides a wealth of information about the nucleus. High-resolution spectroscopy of the tail can identify the specific molecules present, distinguishing between water, carbon dioxide, carbon monoxide, methane, ammonia, and more complex organic compounds. Each molecule has a unique spectral signature, a set of emission or absorption lines at specific wavelengths, allowing for precise chemical identification. For 3I Atlas, such spectroscopy has already confirmed the presence of carbon dioxide in unprecedented quantities. But further observations during perihelion may reveal additional species, particularly if deeper layers of the nucleus are exposed. The detection of complex organic molecules would be of particular interest, as such compounds are the building blocks of life, and their presence in an interstellar object would demonstrate that the chemistry necessary for biology is widespread in the galaxy. The question of whether 3I Atlas will survive its perihelion passage is another source of uncertainty. Some comets, particularly those making their first close approach to the Sun, fragment or disintegrate entirely under the thermal and tidal stresses. The Kreutz family of sun-grazing comets, for example, are thought to be fragments of a much larger comet that broke apart centuries ago. If 3I Atlas is structurally weak, held together only by the tensile strength of its ices, it could break apart as those ices sublimate. Alternatively, if it has a solid, rocky, or metallic core, it will survive, emerging from perihelion, stripped of its volatile envelope, but still intact. The outcome depends on factors we cannot directly observe: the internal structure, the strength of the material, the distribution of ices and rock within the nucleus. We will know the answer only after the fact, when the object emerges from behind the Sun and becomes observable again in the post-perihelion sky. If it survives, astronomers will be watching intently for any changes in its brightness, trajectory, or spectroscopic signature. If it disintegrates, the debris field itself will become a subject of study, providing clues to the object's internal composition and structure. The race against time is not merely a race against the object's trajectory, but a race against the Sun itself, whose light and heat are both the agent of the object's transformation and the barrier to our observation. Thank you for being with us. Please subscribe and leave a like. The implications of 3I Atlas extend far beyond the specifics of this single object. It is the third confirmed interstellar visitor to our solar system, following 1I Oumuamua and 2I Borisov. And each has taught us something profound about the nature of interstellar space and the diversity of objects wandering between the stars. 2I Borisov, discovered in 2019, was in many ways the least controversial of the three. It was clearly a comet, exhibiting a bright coma and tail, a composition dominated by water, ice, and carbon monoxide, and a nucleus estimated to be about 1 kilometer in diameter. Its behavior matched expectations for a comet formed in another stellar system and ejected into interstellar space through gravitational interactions with giant planets. 2I Borisov was reassuring, a confirmation that some interstellar objects are exactly what we expected them to be. Yet even 2I Borisov had its surprises. Spectroscopic observations revealed that its gas composition was somewhat different from solar system comets, with a higher ratio of carbon monoxide to water, suggesting formation in a colder environment. Its dust properties, analyzed through polarimetry, indicated that the dust grains were unusually compact and homogeneous, unlike the fluffy aggregates typical of solar system comets. These subtle differences hinted at the diversity of planetary formation environments across the galaxy. If even a relatively normal interstellar comet shows compositional variations, what might we find in more exotic objects? 1I Oumuamua remains the most enigmatic. Its discovery in October 2017 was serendipitous, detected by the Pan-STARRS telescope in Hawaii during a routine survey of near-Earth objects. Initial observations suggested it was an asteroid, as no coma or tail was visible, but its trajectory clearly indicated an origin outside the solar system. As more data accumulated, its strangeness became apparent. Its light curve, the variation in brightness as it rotated, showed extreme changes, suggesting a highly elongated shape with an axis ratio of at least 5:1, possibly as high as 10:1. No natural asteroid or comet in our solar system has such an extreme shape. Its surface was highly reflective, with a reddish color similar to some outer solar system objects. But the lack of any detectable outgassing was deeply puzzling. Then came the detection of non-gravitational acceleration, a small but statistically significant deviation from a purely gravitational trajectory. For a typical comet, such acceleration is easily explained by the rocket effect of outgassing. But Oumuamua showed no signs of a coma or tail, even in the most sensitive observations. This paradox led to a flurry of papers proposing various explanations. Perhaps it was outgassing hydrogen, which would be invisible to our instruments. Perhaps it was covered in a thick crust that confined outgassing to narrow jets invisible from our viewing angle. Perhaps it was composed of exotic nitrogen ice, sublimating without producing visible dust. Each explanation had its proponents and its difficulties. Dr. Loeb's light sail hypothesis, published with Dr. Bialy in late 2018, proposed that Oumuamua's properties could be explained if it were a thin, flat object, perhaps only a fraction of a millimeter thick, with a large surface area relative to its mass. Such an object would experience significant radiation pressure from the sun, explaining the non-gravitational acceleration without requiring outgassing. The paper carefully noted that if this were the case, the origin could be either natural, perhaps a fragment of a larger body disrupted by tidal forces, or artificial, a piece of technology from an extraterrestrial civilization. The suggestion of an artificial origin, even presented as one possibility among several, generated intense media coverage and equally intense criticism from much of the astronomical community. Critics argued that the hypothesis multiplied assumptions unnecessarily, that natural explanations, while incomplete, were more parsimonious. The debate became polarized, with Dr. Loeb cast as either a visionary willing to consider unconventional ideas or a sensationalist over-interpreting ambiguous data depending on one's perspective. The truth, as always, is that we simply do not know. Oumuamua is gone, beyond recall, and without more data, the question of its nature cannot be definitively resolved. It remains a lesson in humility, a reminder that the universe can present us with phenomena that do not fit neatly into our existing frameworks. 3I Atlas, arriving in this context, inevitably becomes part of the same debate. Its anomalies are different from Oumuamua's, yet they are anomalies nonetheless. The nickel without iron, the extreme carbon dioxide, the rapid morphological changes, all mark it as unusual. The question is whether unusual means alien or merely unfamiliar, a natural object formed under conditions we have not yet fully understood. The scientific process is designed to answer such questions through observation, hypothesis, and testing, but it requires time, data, and the willingness to follow the evidence wherever it leads. The current situation, with 3I Atlas disappearing into the sun's glare just as it undergoes its most dramatic transformation, is frustratingly suboptimal. We are being forced to draw conclusions from incomplete data, to make inferences from fleeting glimpses. It is science under pressure, conducted at the limits of our observational capabilities. The role of space agencies in this process is critical. NASA, ESA, and other national space organizations operate the instruments that provide much of the data on interstellar objects. These agencies are taxpayer-funded, with mandates to conduct scientific research for the public benefit. The expectation, particularly in the era of open data policies, is that observations will be made available to the broader scientific community in a timely manner. Yet the reality is more complex. Raw data from spacecraft instruments often requires extensive calibration and processing before it can be scientifically useful. Detector artifacts must be removed, instrumental effects must be corrected, and the data must be converted into physical units. This process takes time and expertise, and space agencies must balance the demand for rapid data release with the need for accuracy and quality control. The frustration expressed by Dr. Parmeshansan and Adneda Sand, Loeb and others reflects a broader tension in the scientific community about the pace of data release and the accessibility of publicly funded observations. In the specific case of 3I Atlas, the question is whether all available data is being released, and whether the analysis is being conducted with appropriate urgency given the fleeting nature of the observational window. Dr. Loeb's statement that NASA might be keeping secrets is a strong accusation, one that implies either deliberate withholding of data or at minimum a lack of transparency about what observations have been conducted and what results have been obtained. NASA's response, or lack thereof, to such accusations becomes part of the story, shaping public perception of the agency's openness and commitment to scientific inquiry. The reality is likely more mundane. Data exists, but is still being processed. Observations are being conducted, but results are preliminary. And the machinery of institutional science moves more slowly than the rapid pace of online discourse. Yet, in the age of instant communication, such explanations can feel unsatisfying, particularly when the object in question might represent one of the most significant discoveries in human history. The philosophical implications of interstellar objects, particularly if any were confirmed to be artificial, are staggering. For all of human history, we have been alone, or at least believed ourselves to be. Every object in the night sky, every planet, asteroid, and comet we have studied, formed in our solar system, sharing a common origin in the primordial disk of gas and dust that surrounded the young Sunday. The discovery of interstellar objects breaks this isolation. These are pieces of other worlds formed in other stellar systems, now adrift in the vast ocean between stars. They are emissaries from distant places, carrying information about conditions and processes far beyond our direct reach. If they are natural, they tell us about the diversity of planetary systems, the violence of planetary formation and evolution, and the mechanisms by which material is exchanged between stars. If any are artificial, they tell us that we are not alone, that other intelligences have arisen in the cosmos, mastered technology, and sent their creations out into the galaxy. The Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations and the lack of contact with, or evidence for them, looms over this entire discussion. If intelligent life is common in the galaxy, why have we not seen definitive signs of it? The possible answers range from the optimistic, such as that civilizations are common but interstellar travel is difficult, and we simply have not detected their signals yet, to the pessimistic, such as that intelligent civilizations inevitably destroy themselves before achieving interstellar capabilities. The detection of an artificial interstellar object would not fully resolve the paradox, but it would shift the terms of the debate dramatically. It would prove that at least one other civilization achieved the capability to send objects into interstellar space, even if those objects are now defunct or uncrewed. It would tell us that the galaxy has hosted, or still hosts, technological intelligence beyond our own. The burden of proof for such a claim is appropriately high. Carl Sagan's famous dictum, that extraordinary claims require extraordinary evidence, is the guiding principle. A natural explanation for 3I Atlas, no matter how exotic, is always more probable a priori than an artificial explanation, simply because we know that natural processes create vast numbers of comets and asteroids, while we have no confirmed examples of alien technology. The evidence required to overturn this prior probability must be compelling, unambiguous, and resistant to alternative interpretation. The anomalies of 3I Atlas, significant as they are, do not yet reach this threshold. They are suggestive, intriguing, worthy of intense study, but not definitive. The object could be a natural comet with an unusual formation history, a fragment of a differentiated planetary body, a relic of exotic stellar nucleosynthesis, or any number of other natural phenomena we have not yet fully characterized. The scientific community's caution is not closed-mindedness, but appropriate skepticism, the application of Occam's razor to weight competing hypotheses. Yet caution must not become dogma. The history of science is filled with examples of phenomena initially dismissed as impossible or implausible that later proved to be real. Meteorites, the idea that rocks could fall from the sky, were ridiculed by the French Academy of Sciences in the 18th century before overwhelming evidence forced acceptance. Continental drift, proposed by Alfred Wegener in 1912, was rejected by most geologists for decades before the theory of plate tectonics provided the mechanism and evidence to vindicate him. The existence of black holes, predicted by Einstein's equations, was considered a mathematical curiosity by many physicists until observational evidence accumulated in the latter half of the 20th century. Science progresses not by clinging to existing paradigms, but by remaining open to new evidence and willing to revise our understanding when the data demands it. The challenge with interstellar objects is that the evidence is necessarily incomplete, and the observational window is short. We must make judgments based on limited data, always aware that more information might change our conclusions. This is science, at its most uncertain and most exciting, the frontier where our knowledge meets the unknown. The morphological transformation of 3I Atlas, documented in the Nordic Optical Telescope images, is a concrete fact, a physical event captured in time-stamped data. The interpretation of that fact is where science becomes nuanced, where different researchers with different backgrounds and priors can look at the same data and reach different conclusions. For some, the transformation from anti-tail to tail is exactly what one expects from a carbon dioxide-rich comet approaching perihelion, a confirmation that despite its anomalous composition, 3I Atlas is fundamentally a natural object obeying known physical laws. For others, including Dr. Loeb, the transformation is one more data point in a pattern of anomalies that collectively suggests something beyond ordinary cometary behavior. Both perspectives are scientifically legitimate. Both are grounded in the data, and both will be tested as more observations become available. The resolution of this debate will likely come not from 3I Atlas alone, but from the accumulation of data on multiple interstellar objects over coming years and decades. The detection rate of interstellar objects is expected to increase dramatically in the coming years with the advent of new survey telescopes. The Vera-C Rubin Observatory, currently under construction in Chile, will conduct the legacy survey of space and time, imaging the entire visible sky every few nights with unprecedented depth and sensitivity. When it begins operations, it is predicted to detect dozens, perhaps hundreds of interstellar objects per year, transforming our understanding from a handful of individual cases to a statistically meaningful population. With such a population, patterns will emerge. We will be able to determine what fraction of interstellar objects are comet-like versus asteroid-like, what their typical compositions are, how their properties vary, and whether any exhibit characteristics that cannot be explained by natural processes. The question of artificial objects will shift from speculation about individual anomalies to statistical inference about populations. If even 1% of interstellar objects show signs inconsistent with natural formation, That would be a profound discovery demanding explanation. Conversely, if all detected objects fit comfortably within the range of natural variation, the case for artificial visitors would weaken considerably. 3I Atlas, regardless of its ultimate nature, is a harbinger of this future, a preview of the questions we will be asking and the methods we will use to answer them. The scientific infrastructure being developed to study it, the observational protocols, the data analysis techniques, the collaborative networks of researchers, all will be refined and applied to future discoveries. Every interstellar object is a learning opportunity, a chance to improve our understanding of both the visitors themselves and the optimal strategies for studying them. The deadline of October 29, the perihelion date, looms with existential weight. After that date, 3I Atlas will begin its outbound journey, receding from the sun and gradually fading from view. The window for intensive observation will close, and we will be left to analyze whatever data we have managed to collect. There is no second chance, no opportunity for follow-up observations years later. The object will depart the inner solar system and eventually leave the solar system entirely, returning to the interstellar void from which it came. In a very real sense, we are experiencing a unique moment in cosmic history, the brief intersection of Earth's orbit and the trajectory of a visitor from another star system. Such intersections are rare on human timescales, but common on cosmic timescales. The galaxy is old, 13.6 billion years, and stars have been forming and dying. Planets have been coalescing and fragmenting, and debris has been ejected into interstellar space for most of that time. The space between stars is not empty, but filled with a diffuse population of rogue planets, asteroids, comets, and dust grains, all moving on their own independent trajectories through the galactic gravitational field. Occasionally, purely by chance, one of these objects passes through another star system. The frequency of such passages depends on the density of interstellar objects, a quantity we are only beginning to constrain. Based on the 3 confirmed detections so far, and estimates of our observational completeness, astronomers calculate that at any given time, there is likely at least one interstellar object within the orbit of Neptune. Most are too small and faint to detect, but they are there, silent witnesses to the history of other stars. The realization that our solar system is not a closed system, that material from elsewhere is constantly arriving, is conceptually revolutionary. It means that Earth itself has likely been impacted by interstellar material throughout its history. Micrometeorites, tiny particles of dust captured by Earth's atmosphere, have been analyzed, and some show isotopic signatures inconsistent with solar system formation, suggesting an interstellar origin. If interstellar dust reaches Earth, then larger objects, pebbles, boulders, perhaps even kilometer-sized bodies, must also arrive occasionally. The biological implications are speculative, but tantalizing. If interstellar objects can carry organic molecules, and if some of those molecules survive the journey and the impact with Earth, could they have contributed to the origin of life on our planet? The hypothesis of panspermia, that life or its precursors can be transported between worlds, gains plausibility if the transport mechanism is not just local, within a single star system, but galactic, spanning the distances between stars. 3I Atlas, with its carbon dioxide and potential for complex organics, is a test case for these ideas. The spectroscopic detection of organic molecules in its coma would not prove panspermia, but it would demonstrate that the chemical building blocks of life exist in interstellar objects and can survive the journey through space. The composition of the dust particles in the tail, if analyzed in detail, could reveal the presence of prebiotic compounds, molecules like amino acids, nucleobases, or sugars that are essential to terrestrial biochemistry. Such a finding would not be entirely surprising, as complex organics have been detected in meteorites and in the interstellar medium through radio astronomy, but their presence in an interstellar visitor would underscore the universality of organic chemistry and the potential for life-related molecules to be distributed throughout the galaxy. The other side of this coin is the potential hazard posed by interstellar objects. If they arrive frequently, and if some are large, they represent an impact threat that is independent of the well-studied population of near-Earth asteroids and comets. A large interstellar object on a collision course with Earth would approach with a velocity much higher than typical solar system objects, possibly 50 kilometers per second or more, compared to the 20 to 30 kilometers per second typical of near-Earth asteroids. The kinetic energy scales with the square of velocity, meaning an interstellar impactor would deliver far more energy than a solar system object of the same mass. Fortunately, the probability of such an impact is extremely low given the vastness of space and the small cross-sectional area of Earth. The odds of an interstellar object hitting Earth in any given year are estimated to be far lower than the already low odds of a major asteroid impact. Nonetheless, the possibility exists. And as we detect more interstellar objects and better characterize their population, we will refine our understanding of this risk. The more immediate question for 3I Atlas is whether its trajectory after perihelion will bring it close to any planet or moon. Such an encounter would perturb its trajectory, potentially providing additional data through gravitational interactions. If, for example, it were to pass near Venus or Mercury on its outbound journey, the gravitational deflection could be measured, providing an independent constraint on its mass. The trajectory data, combined with brightness and spectroscopic observations, allow astronomers to infer the object's size, albedo, and mass, though with significant uncertainties. The nucleus of 3I Atlas is estimated to be a few hundred meters to perhaps a kilometer in diameter, but this is based on indirect inference from its brightness and assumptions about its reflectivity. Direct imaging of the nucleus is not possible at the current distance, as it is lost within the glare of the coma. Only after perihelion, if the object survives and activity diminishes, might the bare nucleus become observable, providing a direct measurement of its size and shape. The anti-tail-to-tail transformation documented by Dr. Loeb's team is scientifically valuable, precisely because it provides a time-resolved record of the object's response to changing solar conditions. By correlating the timing of the transformation with the object's distance from the sun and the intensity of solar radiation, researchers can model the sublimation rate of the ices and the dynamics of dust ejection. Such models are foundational to cometary science, refined over decades of studying solar system comets, and their application to an interstellar object tests their generality. If the models work, if they accurately predict the observed behavior, it confirms that despite the unusual composition, the underlying physics is the same. If the models fail, if the observations cannot be explained by standard cometary processes, it suggests that something more exotic is occurring, whether that be an unusual internal structure, an unexpected heat source, or active processes beyond simple sublimation. The diversity of cometary behavior in the solar system is itself a reminder that even natural objects can be surprising. Some comets exhibit outbursts, sudden dramatic increases in brightness caused by the exposure of fresh, volatile, rich material or the collapse of surface structures. Others split into multiple fragments, either due to tidal forces during close solar approaches or due to rotational stresses if they are spinning rapidly. The Great Comet of 1680 passed so close to the Sun that its surface temperature reached thousands of degrees, yet it survived. While Comet Shoemaker-Levy 9 was torn apart by Jupiter's tidal forces in 1992 and subsequently impacted the planet in 1994, creating spectacular fireballs visible from Earth. Comets can be fragile or robust, predictable or capricious, and each one teaches us something about the complex interplay of composition, structure, and environmental forces. 3I Atlas, as an interstellar comet, adds the dimension of foreign origin to this already complex picture. The methods used to study it are the same methods applied to solar system comets: photometry to measure brightness, spectroscopy to identify composition, astrometry to track position and determine trajectory, and polarimetry to characterize dust properties. Yet the interpretation must account for the possibility that its formation environment was fundamentally different, that the conditions in its home stellar system, the temperature, pressure, radiation field, and available materials, were unlike those in our own system's history. This makes every comparison provisional, every inference tentative, and every conclusion subject to revision as more data arrives. The role of Dr. Avi Loeb in this narrative is itself significant. As a prominent astrophysicist with a chair at Harvard and a lengthy publication record in areas ranging from cosmology to black holes to the search for extraterrestrial intelligence, his advocacy for considering the artificial origin hypothesis carries weight even when many of his peers disagree. He has become the public face of the argument that interstellar objects deserve serious consideration as potential artifacts, and his willingness to engage with media and public audiences has brought these questions to a much wider audience than they might otherwise reach. This visibility is a double-edged sword. On one hand, it generates public interest in space science, inspires young people to pursue astronomy, and ensures that funding agencies and policymakers are aware of the importance of detecting and studying interstellar objects. On the other hand, it risks oversimplifying complex scientific debates, creating false dichotomies between natural and artificial explanations, and generating unrealistic expectations about the pace and certainty of scientific discovery. The tension between scientific caution and public communication is a perennial challenge, particularly for topics that touch on profound questions about humanity's place in the universe. Dr. Loeb's critics argue that his public statements often go beyond what the data support, that he frames uncertainties as mysteries and anomalies as evidence in ways that mislead non-specialist audiences. His supporters counter that science progresses through bold hypotheses, that conservatism can become complacency, and that the public has a right to know about ongoing scientific debates, even when conclusions are uncertain. Both perspectives have merit, and the debate itself is healthy, a sign that the scientific process is functioning as it should, with hypotheses being proposed, scrutinized, and tested. The ultimate arbiter is the data, and as more interstellar objects are detected and studied, the weight of evidence will tilt toward one interpretation or another. The claim that NASA is withholding data is more troubling, if true, because it touches on issues of scientific integrity and public trust. NASA operates under policies that require the timely release of data from its missions, typically within a year of collection, to ensure that publicly funded research is accessible to the broader scientific community. If data on 3I Atlas exists and has not been released, the question is why? Is it still being processed and validated, a routine part of the scientific workflow? Is there concern about the quality or interpretation of the data? A desire to avoid releasing preliminary results that might be misleading? Or is there, as Dr. Loeb implies, a reluctance to release data that might challenge conventional explanations or generate controversy? Without access to internal communications and decision-making processes at NASA, it is impossible to know. What is clear is that the allegation has been made, and it adds a layer of institutional intrigue to the scientific mystery of the object itself. The transparency of scientific institutions is not merely a bureaucratic concern, but a foundational principle of the modern scientific enterprise. Science advances through the collective scrutiny of data. The ability of independent researchers to examine observations, replicate analyses, and propose alternative interpretations. When data is withheld, intentionally or through bureaucratic delay, this process is impaired. The concern is particularly acute for time-sensitive phenomena, like interstellar objects, where the observational window is narrow and opportunities for follow-up may be lost forever. If critical data from spacecraft observations of 3I Atlas exists but remains inaccessible to the broader research community, it represents a missed opportunity for collaborative science at precisely the moment when such collaboration is most needed. The question of what constitutes sufficient evidence for an extraordinary claim is itself a matter of philosophical and methodological debate within science. The Bayesian approach, which Dr. Loeb often invokes, treats evidence as a process of updating prior probabilities based on new observations. In this framework, even a low probability hypothesis like artificial origin can become more probable if the observations are sufficiently inconsistent with high probability natural explanations. The challenge is quantifying these probabilities and agreeing on what constitutes sufficient inconsistency. Different researchers, even looking at identical data, can reach different conclusions based on their assessment of prior probabilities and the strength of various lines of evidence. This subjectivity is not a flaw, but an inherent feature of scientific inference, particularly when dealing with unique, non-repeatable phenomena. The ideal resolution would be additional data that definitively favors one explanation over others, but in practice, such definitive data is often unavailable, and we must make judgments under uncertainty. The legacy of 3I Atlas will ultimately be determined not by its true nature, which may remain ambiguous, but by what it teaches us about the process of studying interstellar visitors and the questions we should ask of future objects. The observational campaigns, the collaborative networks, the analytical techniques, the public engagement, all represent a learning process that will benefit future investigations. Each interstellar object is a test case, refining our methods and sharpening our questions. The debate over natural versus artificial origin, while currently focused on a small number of objects, is preparing the scientific community for a future in which such objects are detected regularly. When that future arrives, we will need established protocols for rapid follow-up, agreed-upon criteria for anomalous behavior, and transparent processes for data sharing and analysis. The controversies surrounding 3I Atlas and its predecessors are helping to define those protocols and criteria, ensuring that when the next object arrives, we are better prepared to study it effectively. The perihelion passage on October 29 is not merely a calendrical milestone, but a physical crucible, the moment when 3I Atlas experiences maximum stress and maximum transformation. The object's response to this extreme environment will reveal aspects of its structure and composition that are invisible under more benign conditions. If it fragments, the pieces will provide a cross-section through its interior, exposing materials that were previously buried beneath the surface. If it survives intact, the post-perihelion observations will show whether the nucleus is still active, still producing a coma and tail, or whether it has been stripped of volatiles and rendered inert. The brightness of the object in the days following perihelion will be closely monitored, as any deviation from predicted values could indicate unexpected mass loss, surface changes, or residual outgassing. The spectroscopic signature will be analyzed for changes in composition, particularly the appearance of new molecular species that might be released from deeper layers. The trajectory will be measured with high precision to detect any non-gravitational forces, and the magnitude of those forces will be used to estimate the rate of mass loss and the efficiency of the rocket effect. Every observation is a piece of a larger puzzle, and the full picture will only emerge when all the pieces are assembled and analyzed in the context of theoretical models. The concept of an interstellar object as a messenger is not merely poetic, but scientifically precise. These objects carry information encoded in their physical properties. Their composition records the chemistry of their formation environment. Their structure reflects the mechanical processes that shape them. Their trajectory preserves a memory of the gravitational interactions that ejected them from their home system. Reading this message requires sophisticated instruments and careful analysis, but the information is there, waiting to be decoded. In the case of 3I Atlas, the message is still being received, still being interpreted, and the final translation will require months or years of work, even after the object itself has departed. Scientific papers will be written, data will be archived, models will be refined, and debates will continue. This is the normal pace of science, slower than the breathless pace of news cycles, but ultimately more reliable, more thorough, and more self-correcting. The public narrative of 3I Atlas, shaped by press releases, blog posts, and media coverage, is necessarily simplified, focusing on dramatic highlights and clear dichotomies. The scientific narrative, embedded in peer-reviewed publications and technical reports, is more nuanced, more cautious, and more tentative. Both narratives have their place, and both contribute to the broader cultural conversation about our place in the cosmos. The challenge is maintaining fidelity to the underlying science while communicating its excitement and significance to non-specialist audiences. This requires skill, integrity, and a willingness to embrace uncertainty as a feature rather than a bug of the scientific process. The philosophical implications of discovering an artificial interstellar object would extend far beyond science. It would force a re-evaluation of humanity's cosmic significance, confirming that intelligence and technology are not unique to Earth. It would raise immediate practical questions about the origin, purpose, and potential hazards of such objects. It would energize efforts to search for extraterrestrial intelligence through radio and optical SETI, as the existence of artifacts would imply the existence of their creators. It would also raise profound questions about why such objects are not more common, why we have not detected obvious signs of widespread technological activity in the galaxy. The answers to these questions would reshape fields from astrobiology to philosophy, from planetary defense to interstellar exploration. Yet all of this remains hypothetical, contingent on evidence that has not yet reached the threshold of scientific acceptance. The appropriate stance is open-minded skepticism, willing to consider extraordinary possibilities, but insisting on extraordinary evidence, recognizing that nature is capable of producing phenomena that mimic our expectations for technology. The history of astronomy is replete with examples of natural phenomena initially mistaken for artificial pulsars, briefly considered as possible beacons from extraterrestrial civilizations, turned out to be rapidly rotating neutron stars. The WOW signal, a strong narrowband radio signal detected in 1977 and never repeated, remains unexplained, but is more likely a natural transient than a deliberate transmission. The lesson is that initial anomalies often resolve into natural explanations as more data becomes available, and that caution is warranted before invoking intelligence as an explanation. At the same time, caution must not become dogma. If the evidence genuinely points toward an artificial origin, if natural explanations become increasingly contrived and implausible, then the hypothesis must be taken seriously. The scientific community's task is to weight the evidence fairly, without bias toward either conventional or unconventional explanations, and to update beliefs as new data warrants. The current state of evidence for 3I Atlas does not, in the assessment of most astronomers, reach the threshold for invoking an artificial origin. The anomalies are real but explicable within the framework of natural cometary science, albeit at the edges of our current understanding. Dr. Loeb's continued advocacy for considering the artificial hypothesis is valuable as a spur to thorough investigation, ensuring that all possibilities are explored and that data is scrutinized with appropriate rigor. Even if the hypothesis is ultimately rejected, the process of considering and testing it strengthens the scientific case for the natural explanation, demonstrating that alternative interpretations have been seriously evaluated and found wanting. The final weeks of 3I Atlas's close approach to the Sun will be critical. Observations from coronagraphs aboard SOHO, Stereo, and Solar Orbiter will track the object through perihelion, documenting its brightness evolution and searching for signs of fragmentation. Ground-based telescopes will resume observations as soon as the object emerges from the solar glare, measuring its post-perihelion properties and comparing them to pre-perihelion baselines. The data from these observations will be archived, analyzed, and published, contributing to the permanent scientific record. Years from now, when more interstellar objects have been detected and studied, researchers will look back at 3I Atlas as an early example, a learning experience that shaped subsequent investigations. The object itself, indifferent to our scrutiny, will continue on its trajectory, exiting the solar system and returning to the interstellar medium. It will travel for millions of years, potentially encountering other star systems, perhaps being detected by other civilizations if such exist, or perhaps wandering in isolation until the end of time. Its brief passage through our system is a momentary intersection of two cosmic trajectories, ours and its own, a chance encounter in the vastness of space. The mystery of its origin, whether resolved or enduring, is ultimately less important than what it represents. The opening of a new era in astronomy, the era of interstellar visitors. For millennia, humans have looked at the stars and wondered what lies beyond our own celestial neighborhood. Now, pieces of that beyond are coming to us, and we are learning to read their stories. The transformation of the anti-tail into a tail, documented in real time by the Nordic Optical Telescope, is a chapter in that story, a visible sign of the object's response to the Sun's influence. Whether that response is the sublimation of exotic ices, the venting of pressurized gases, or something entirely unexpected, it is a natural experiment, a test of our understanding conducted on a cosmic stage. The results of that experiment will be published, debated, and eventually synthesized into a broader understanding of cometary science and interstellar objects. The process is slow, methodical, and subject to revision. But it is also cumulative, building knowledge step by step, observation by observation. This is how science works, not through sudden revelations or definitive proofs, but through the patient accumulation of evidence and the gradual refinement of understanding. The narrative of 3I Atlas, told here in the form of accessible science communication, is necessarily incomplete, a snapshot of an ongoing investigation. The final chapter has not been written because the observations are not yet complete, the data not yet fully analyzed, the papers not yet published. What we have is a mystery in progress, a scientific thriller unfolding in real time, with the outcome still uncertain. The transformation from anti-tail to tail is a clue, a piece of evidence, but its meaning depends on context, on additional observations, on theoretical modeling. The allegation of data withholding is a subplot, a question of institutional transparency that may or may not be resolved. The hypothesis of artificial origin is a provocative possibility, a challenge to conventional thinking that ensures thorough scrutiny of all available data. Together, these elements create a narrative rich in suspense, scientific intrigue, and philosophical depth, a story that engages both the intellect and the imagination. As 3I Atlas approaches its moment of closest encounter with the Sun, we are reminded of the fragility and transience of our observational opportunities. The universe presents us with phenomena on its own schedule, indifferent to our readiness or capability. Our task is to observe as carefully as possible, to analyze as rigorously as possible, and to remain open to whatever the data reveals. The story of 3I Atlas is ultimately the story of humanity's encounter with the unknown. Our attempt to understand our place in a cosmos far stranger and more diverse than we once imagined. Whether the object is a natural comet or something more exotic, it has already succeeded in expanding our horizons, challenging our assumptions, and reminding us that the universe still holds secrets worth discovering. The journey continues, the data accumulates, and the mystery deepens, all while a small, faint object rushes toward the Sun, carrying within it answers we have not yet learned to read. The scientific infrastructure required to detect and study interstellar objects represents decades of investment in astronomical technology and international collaboration. The Pan-STARRS telescope that discovered 1I Oumuamua, the telescopes that tracked 2I Borisov, and now the Nordic Optical Telescope capturing the transformation of 3I Atlas, all are part of a global network of observatories dedicated to surveying the sky and monitoring transient phenomena. These facilities operate continuously, scanning vast regions of the sky night after night, accumulating terabytes of data that must be processed, analyzed, and searched for anomalies. The detection of an interstellar object is often serendipitous, a byproduct of surveys designed for other purposes, such as searching for near-Earth asteroids or studying variable stars. Once detected, however, the full power of the astronomical community can be brought to bear, with telescopes around the world and in space coordinating observations to maximize coverage and data quality. This collaborative model is essential because interstellar objects move rapidly across the sky, fading as they recede from the Sun, and no single observatory can maintain continuous coverage. The data from multiple observatories must be combined, calibrated, and analyzed together to extract maximum scientific value. The expertise required spans multiple disciplines: astrometry for precise position measurements, photometry for brightness determination, spectroscopy for compositional analysis, and orbital dynamics for trajectory calculation. Each discipline contributes a piece of the puzzle, and only by integrating all pieces can a complete picture emerge. The challenge of studying 3I Atlas is compounded by its current position in the sky. Objects near the Sun in the dayside sky are difficult to observe from ground-based telescopes because they must be observed during twilight or daylight hours. When the sky is bright and atmospheric, seeing conditions are poor. The contrast between the faint light of the comet and the overwhelming brightness of the sky makes detection and measurement extremely challenging. Specialized techniques, such as observing at high altitudes where the atmosphere is thinner and using narrowband filters to isolate specific emission lines, can improve sensitivity, but fundamental limitations remain. This is where space-based observatories become crucial. Instruments above Earth's atmosphere, particularly those designed to observe the sun's corona, can block the direct solar light while remaining sensitive to fainter nearby objects. The coronagraphs aboard SOHO and Stereo are optimized for this purpose, using occulting disks to create an artificial eclipse, allowing the faint corona and any comets passing nearby to be observed. These instruments have discovered thousands of sun-grazing comets over the past decades, most of them small fragments of larger bodies that disintegrate as they plunge toward the Sunday 3I Atlas. While much larger and more distant from the sun than typical sun grazers, still benefits from coronographic observation during its perihelion passage. The challenge is that coronagraphs are designed for specific brightness ranges and angular separations from the sun, and an object, like 3I Atlas, may fall outside the optimal observing parameters. The observations must be carefully planned, with predictions of the object's position and brightness used to determine the optimal times and instrument settings. Any detection is then carefully analyzed to separate the genuine signal of the comet from instrumental artifacts and background noise. The data quality from such observations is often lower than from dedicated comet observations under ideal conditions, but it is invaluable because it provides the only information available during the critical perihelion period. The composition of 3I Atlas, particularly the dominance of carbon dioxide over water ice, has profound implications for understanding its formation environment. In the solar system, water ice is the most abundant volatile in comets because water is the most abundant molecule in the universe after hydrogen and helium, and it condenses readily in the cold outer regions of protoplanetary disks. Carbon dioxide is also present, but typically in smaller quantities because much of the carbon is locked up in carbon monoxide or methane, depending on temperature and chemical conditions. The high carbon dioxide abundance in 3I Atlas suggests either a formation region, even colder than the outer solar system, where carbon dioxide ice is more stable than water ice, or a formation process that preferentially incorporated carbon dioxide, perhaps through chemical reactions on dust grain surfaces in a dense molecular cloud. Another possibility is that the object formed in a protoplanetary disk around a star with unusual elemental abundances, enriched in carbon relative to oxygen compared to our Sunday. Such stars exist, classified as carbon stars, and their planetary systems would have compositions reflecting this unusual chemistry. Objects forming in such systems might indeed have high carbon dioxide and other carbon-rich compounds while being depleted in water. The nickel without iron anomaly could similarly reflect unusual elemental abundances in the parent star or formation region. These are speculative explanations, but they are grounded in known astrophysical processes and represent the kind of exotic but natural scenarios that could account for 3I Atlas's unusual properties. Testing these scenarios requires detailed modeling of chemical and physical processes in protoplanetary disks, incorporating variations in temperature, pressure, elemental abundance, and radiation fields. Such models are complex, involving gas phase chemistry, surface chemistry on dust grains, ice sublimation and condensation, and the dynamics of disk evolution. The results are sensitive to assumptions and initial conditions, meaning that multiple models can often fit the same observations, making it difficult to discriminate between them. This ambiguity is frustrating but unavoidable when studying distant phenomena that cannot be directly sampled or experimentally reproduced. The best approach is to gather as much observational data as possible, constraining the models as tightly as the data allows, and remaining open to revising interpretations as new observations become available. The comparison between 3I Atlas and solar system comets is instructive because it highlights both similarities and differences. Like solar system comets, 3I Atlas exhibits a coma and tail, undergoes brightening as it approaches the Sun, and shows spectroscopic evidence of volatile sublimation. These similarities suggest that the basic physics of cometary activity, driven by solar heating and ice sublimation, operates similarly in interstellar objects. The differences, particularly the compositional anomalies, indicate that while the physics is similar, the chemistry can vary significantly depending on formation conditions. This pattern is exactly what one would expect if interstellar objects are natural bodies formed in diverse stellar environments across the galaxy. Each stellar system has its own unique conditions, shaped by the mass and composition of the parent star, the architecture of the planetary system, the history of dynamical interactions, and the environment of the surrounding molecular cloud. Objects ejected from these systems carry the signature of their origins, providing a sample of the diversity of planetary formation processes occurring throughout the galaxy. In this view, interstellar objects are not just curiosities, but scientific treasures. Each one a natural experiment, revealing conditions and processes inaccessible through other means. The value of studying them extends beyond the objects themselves to the broader understanding of planet formation, stellar chemistry, and galactic evolution. The potential for 3I Atlas to carry organic molecules, the building blocks of life, adds another dimension to its significance. Organic chemistry is ubiquitous in space, detected in molecular clouds, in protoplanetary disks, in asteroids and comets, and in the atmospheres of planets and moons. The molecules range from simple species like methane and ethane to complex chains and rings containing dozens of atoms. Some, like amino acids and nucleobases, are directly relevant to terrestrial biology, raising the question of whether life's origins on Earth were seeded by delivery of organic material from space. The hypothesis of exogenesis, that life's building blocks came from space, is supported by the detection of amino acids in meteorites, particularly carbonaceous chondrites, which contain a rich inventory of organic compounds. If interstellar objects also carry such compounds, it suggests that organic chemistry is a universal phenomenon, occurring wherever the necessary elements and energy sources are present. The detection of such molecules in 3I Atlas would require high-resolution spectroscopy, capable of identifying the characteristic absorption or emission lines of complex organic species. Such observations are challenging because organic molecules have complex spectra with many overlapping features, and the signals are often weak, requiring long integration times and sensitive instruments. Nonetheless, the scientific payoff would be substantial, demonstrating that the chemistry of life extends beyond our solar system and confirming that the ingredients for biology are distributed throughout the galaxy. The trajectory of 3I Atlas, its path through the solar system, is itself a source of information. The object's orbital elements, the parameters that describe its path through space, indicate an origin from a specific direction in the galaxy. By tracing the trajectory backward, astronomers can estimate where the object came from, though the uncertainties grow rapidly with time due to the cumulative effects of gravitational perturbations from stars and molecular clouds along the path. Over millions of years, these perturbations scramble the trajectory, making it impossible to identify a specific parent star system. Nonetheless, the general direction provides clues about the object's origin, whether it came from the galactic disk, the halo, or some intermediate region. The velocity of the object relative to the local standard of rest, The average motion of stars in the solar neighborhood can indicate whether it was ejected from a young stellar system with high velocity or drifted for eons as part of the general interstellar population. These kinematic clues, combined with compositional data, help build a narrative of the object's history, its formation, ejection, and journey through interstellar space. The age of 3I Atlas, the time since it was ejected from its parent system, is impossible to determine directly, but can be constrained by its dynamical and physical properties. If the object shows signs of recent activity or fresh, unweathered surfaces, it suggests a relatively recent ejection within the last few million years. If it appears heavily processed by cosmic rays and micrometeorite impacts, it suggests a much older object, possibly billions of years old, that has wandered the galaxy for a significant fraction of the age of the Milky Way. The cosmic ray exposure age, determined by measuring isotopic ratios produced by cosmic ray bombardment, is a technique used on meteorites and could in principle be applied to interstellar objects if samples could be obtained. Without samples, such measurements are impossible, and age estimates remain highly uncertain. The question of whether 3I Atlas represents a common or rare type of interstellar object is important for understanding the population as a whole. If objects with similar anomalous compositions are frequently detected in future surveys, it suggests that such compositions are typical of certain formation environments and that our solar system's chemistry is not universal. If 3I Atlas is unique or extremely rare, it suggests either a very unusual formation scenario or possibly a non-natural origin. The statistical analysis of the interstellar object population, once sufficient numbers have been detected, will address this question directly. For now, with only 3 confirmed detections, it is premature to draw firm conclusions about the population characteristics. Each object is treated as an individual case study, analyzed in detail and compared to theoretical expectations. The accumulation of such case studies will eventually reveal patterns and allow for population-level inferences. The interstellar medium, the space between stars, is not a perfect vacuum, but a tenuous mix of gas, dust, and high-energy particles. Objects traveling through this medium for millions or billions of years are subjected to constant bombardment by cosmic rays, exposure to ultraviolet and X-ray radiation, and collisions with dust grains. These processes gradually alter the surface properties of the object, creating a weathered rind that may be compositionally and structurally different from the pristine interior. The study of space weathering on solar system objects, particularly asteroids and airless bodies like the Moon, has revealed the importance of these processes in modifying surface properties. For interstellar objects, the effects may be even more pronounced due to the longer exposure times and potentially higher flux of energetic particles in interstellar space compared to the relatively sheltered environment of the solar system. The transformation of surface ices through radiolysis, the breaking of chemical bonds by radiation, can create new molecular species and alter the volatility and appearance of the surface. Amorphous ice can be converted to crystalline ice, or organic compounds can be synthesized from simpler precursors. These processes complicate the interpretation of spectroscopic observations because the observed surface may not be representative of the bulk composition. The sublimation of surface ices as the object approaches the Sun can expose deeper, less processed material, providing a window into the pristine interior composition. This is one reason why perihelion observations are so valuable. They reveal layers that were previously hidden, offering a more complete picture of the object's makeup. The dust particles ejected from 3I Atlas and forming the tail are themselves subjects of intense scientific interest. The size distribution, shape, Composition and optical properties of these particles can be determined through detailed photometric and polarimetric observations. Dust particles scatter sunlight, and the way they scatter depends on their size, shape, and refractive index. By measuring the brightness and polarization of scattered light at multiple wavelengths and viewing angles, astronomers can infer the dust properties. This technique has been applied extensively to solar system comets and is now being used to study interstellar object dust. The findings reveal whether the dust is similar to that in solar system comets, composed primarily of silicate minerals and organic compounds, or whether it has unusual properties suggesting a different origin or processing history. The discovery of unusual dust properties would be another piece of evidence for the exotic nature of 3I Atlas, while similarity to solar system comet dust would support a natural cometary origin. The balance of evidence thus far leans toward a natural explanation, but with significant uncertainties and anomalies that keep the question open. The public fascination with 3I Atlas and interstellar objects more broadly reflects deep-rooted human curiosity about the cosmos and our place within it. The possibility, however remote, that we might be observing evidence of extraterrestrial technology taps into fundamental questions about whether we are alone in the universe. These questions have motivated centuries of speculation, from the ancient Greeks pondering the plurality of worlds to modern SETI programs scanning the skies for radio signals. The detection of an artificial interstellar object would be a SETI success of a different kind, not a deliberate signal but an artifact, a piece of technology that has drifted into our detection range. The distinction between detecting a signal and detecting an artifact is significant. Signals require intentional transmission, a decision by the sender to communicate, while artifacts could be ancient, derelict, or unintentional emissions from technology not designed to be detected. The latter scenario might be more probable if technological civilizations are common, but long-lived civilizations are rare, leaving behind debris that outlasts the civilizations themselves. This dystopian vision of a galaxy littered with the remnants of extinct civilizations is one possible resolution of the Fermi paradox, but it remains speculative in the absence of any confirmed detections. The search for technosignatures, evidence of technology beyond Earth, has expanded in recent years to include not just radio and optical signals, but also atmospheric signatures of industrial pollutants, megastructures like Dyson spheres, and indeed anomalous interstellar objects. The field is maturing from a fringe pursuit to a recognized area of astrobiology, with NASA and other agencies now funding technosignature research as a legitimate scientific endeavor. This shift reflects a growing recognition that the question of extraterrestrial intelligence is not merely philosophical, but empirically testable, and that the tools and methods of astronomy can be applied to search for evidence. The challenge is distinguishing genuine technosignatures from natural phenomena, a task that requires extremely high standards of evidence and rigorous skepticism. False positives, natural phenomena, mistaken for technology, are far more likely than true positives, simply because we know natural phenomena are common while we have no confirmed examples of extraterrestrial technology. Every claimed detection must withstand intense scrutiny and survive attempts at falsification before it can be accepted. The case of 3I Atlas illustrates this process. Anomalies are identified, alternative explanations are proposed and tested, and the scientific community debates the strength of evidence. This is exactly how science should work, and regardless of the ultimate conclusion about 3I Atlas, the process itself is valuable, refining our methods and preparing us for future discoveries. The role of computational modeling in understanding 3I Atlas cannot be overstated. Modern astrophysics relies heavily on computer simulations to test hypotheses and predict observational signatures. For interstellar objects, models simulate the thermal evolution of the nucleus as it approaches the Sun, calculating surface temperatures, sublimation rates, and the resulting gas and dust production. These models incorporate the object's orbital trajectory, its size and shape, its thermal properties, and the composition of its ices. The output is a prediction of how the object should brighten, what its spectrum should look like, and how its coma and tail should develop. These predictions are then compared to actual observations, and discrepancies between model and data indicate either that the input parameters need adjustment or that the physical processes included in the model are incomplete. Iterative refinement of the models, guided by observational feedback, gradually improves their accuracy and predictive power. For 3I, Atlas, existing cometary models provide a starting point, but the unusual composition, particularly the dominance of carbon dioxide, requires modifications to standard assumptions. The sublimation temperature and latent heat of carbon dioxide differ from those of water ice, affecting the thermal evolution and outgassing behavior. Models must account for these differences to accurately predict the object's activity. The agreement or disagreement between model predictions and observations then becomes a test of whether the object can be understood within the framework of natural cometary science or whether additional exotic processes must be invoked. So far, with appropriate adjustments for composition, models have been reasonably successful in explaining 3I Atlas's behavior, supporting the natural comet hypothesis. However, the story is not yet complete, and post-perihelion observations may reveal surprises that challenge current models. The concept of planetary defense, protecting Earth from asteroid and comet impacts, has grown in prominence over the past decades, driven by the recognition that while the probability of a major impact in any given year is low, the consequences would be catastrophic. Programs like NASA's Planetary Defense Coordination Office and ESA's Space Situational Awareness Program monitor near-Earth objects, calculate impact probabilities, and develop mitigation strategies. The arrival of interstellar objects adds a new dimension to this challenge because their high velocities and unpredictable trajectories make them difficult to track and potentially more dangerous. An interstellar impactor would deliver far more energy than a typical near-Earth asteroid of the same size, and the warning time might be shorter if the object is not detected until it is already close to Earth. Fortunately, the cross-sectional area of Earth is tiny compared to the vastness of space, and the probability of an interstellar object on a collision course is vanishingly small. Nonetheless, as detection capabilities improve and more interstellar objects are discovered, the planetary defense community is beginning to consider how to incorporate them into risk assessments and contingency planning. The detection and tracking of interstellar objects also has implications for future space missions. If such objects are relatively common, there may be opportunities to send spacecraft to intercept and study them at close range, or even to return samples to Earth. Such missions would be technically challenging due to the high relative velocities involved, requiring either very fast spacecraft or carefully planned trajectories that match the object's velocity. The scientific payoff, however, would be enormous, providing direct physical and chemical analysis that is impossible from remote observations alone. Mission concepts for intercepting interstellar objects have been proposed, including high-speed flyby missions that would gather data during a brief close encounter, and more ambitious rendezvous missions that would match the object's velocity and accompany it for an extended period. The feasibility of such missions depends on early detection, giving mission planners sufficient lead time to design, build, and launch a spacecraft. The upcoming Vera Rubin Observatory, with its ability to detect interstellar objects years before they reach the inner solar system, could provide the necessary warning, opening the door to dedicated interstellar object missions in the coming decades. The scientific return from such a mission, particularly if it could confirm or refute the artificial origin hypothesis for a specific object, would justify the substantial investment required. The transformation of 3I Atlas from an antitail to a tail configuration, while seemingly a minor morphological detail, encapsulates the broader challenge of interpreting ambiguous data. Is this transformation a natural consequence of changing viewing geometry and outgassing patterns? Or does it indicate something more fundamental about the object's structure or behavior? The answer lies in detailed modeling and analysis, comparing the observed morphology to predictions for various scenarios. An antitail, as mentioned earlier, is typically an optical effect caused by large dust particles that lag behind the nucleus in its orbit, creating a spike that appears to point toward the Sun from our perspective on Earth. As the viewing geometry changes, this spike can rotate and evolve, potentially becoming aligned with or merging into the main dust tail. Alternatively, changes in the dust production rate or the size distribution of particles could alter the appearance of the tail structure. High-resolution imaging over time, capturing the evolution of the tail morphology, allows astronomers to discriminate between these possibilities. The Nordic Optical Telescope images provide a snapshot of this evolution, documenting the state of the object at a specific moment, but additional observations before and after are needed to fully understand the transition. The temporal resolution of observations is limited by telescope availability, weather, and the object's position in the sky, meaning that some aspects of the evolution may be incompletely sampled. This is an inherent limitation of astronomical observations. We cannot control the phenomena we study, cannot repeat experiments, and must work with whatever data we can obtain given practical constraints. Despite these limitations, the accumulated observations of 3I Atlas represent a substantial data set, and the analysis of this data is ongoing, with results appearing in scientific publications and conference presentations. The peer review process ensures that claims are thoroughly vetted before being accepted by the broader community, and alternative interpretations are debated in the literature. The narrative of scientific discovery is rarely linear or tidy. It involves false starts, contradictory results, heated debates, and gradual convergence toward consensus as evidence accumulates. The case of 3I Atlas exemplifies this messy reality, with competing interpretations, allegations of data withholding, and fundamental uncertainties about the object's nature. This messiness is not a failure of science, but a feature of the process, particularly when dealing with frontier questions where existing frameworks may be inadequate. The history of science shows that major advances often come from anomalies that do not fit established paradigms, forcing revisions and expansions of theory. Whether 3I Atlas represents such an anomaly, or merely an unusual but explicable natural object, remains to be determined. The important point is that the scientific community is engaged with the question, collecting data, testing hypotheses, and following the evidence. This engagement is what distinguishes science from dogma or speculation, the commitment to empirical investigation, and the willingness to revise beliefs in light of new evidence. The October 29 perihelion date represents a deadline not just for the object's closest approach, but for the observational campaign. After perihelion, the object will recede from the Sun, gradually fading as the solar heating decreases and outgassing subsides. The post-perihelion observations will be crucial for assessing how the object has changed, whether it survived intact, and what its final trajectory will be. The non-gravitational acceleration, if present, will cause deviations from a purely gravitational orbit, and measuring these deviations provides constraints on the outgassing rate and the distribution of active areas on the nucleus. High-precision astrometry, measuring the object's position to sub-arcsecond accuracy, allows these tiny deviations to be detected. The challenge is that non-gravitational forces are small compared to solar and planetary gravity, and their effects accumulate slowly over time, requiring extended baselines of observations to measure reliably. For 3I Atlas, the observational baseline extends from its initial discovery months ago through the perihelion passage and will continue for weeks or months afterward, as long as the object remains detectable. The full trajectory solution, incorporating all available data, will be published in due course, providing the definitive orbit and constraints on non-gravitational effects. The legacy of this observational campaign will inform future studies, establishing best practices for tracking and characterizing interstellar objects. The question of what happens to 3I Atlas after it leaves the solar system is both straightforward and profound. Straightforward because the trajectory is determined by gravity and any non-gravitational forces can be calculated. The object will continue on its hyperbolic orbit, exiting the solar system and returning to interstellar space, never to return. Profound, because the object will continue its journey through the galaxy for millions or billions of years, potentially encountering other stellar systems, perhaps being detected by other observers if intelligent life exists elsewhere. From our perspective, it will fade from view, becoming too faint and distant to observe, and eventually passing beyond the reach of even our most powerful future telescopes. The information we have gathered during its brief passage through our system is all we will ever have, a finite data set that must be extracted for maximum scientific value. This finality adds urgency to the current observational campaign and underscores the importance of data preservation and open access. The observations of 3I Atlas are not just for current researchers, but for future scientists who may have new analytical tools, better models, or different perspectives that could extract additional insights from the data. Archiving the data in accessible formats with proper documentation ensures that it remains a resource for the scientific community indefinitely. The broader context of interstellar object studies is the emerging field of comparative planetology on a galactic scale. For decades, planetary science has been limited to our own solar system, with detailed observations of planets, moons, asteroids, and comets that formed from the same primordial material 4.6 billion years ago. The discovery of exoplanets around other stars has expanded this perspective, revealing the diversity of planetary systems and challenging many assumptions about planet formation. However, exoplanet observations are limited to bulk properties like mass, radius, and atmospheric composition, inferred from indirect techniques like transits and radial velocity measurements. We cannot yet visit exoplanets, cannot study their surfaces or interiors, cannot sample their materials. Interstellar objects offer a complementary approach. They are samples from other planetary systems that have come to us, allowing detailed study with the same techniques applied to solar system objects. Each interstellar object is a piece of an exoplanetary system, carrying information about its formation and evolution. The accumulation of data from multiple interstellar objects will eventually allow statistical comparisons, revealing whether our solar system is typical or unusual in its composition and architecture. This comparative approach will address fundamental questions about planet formation. Is the process universal, producing similar outcomes everywhere? Or does it vary significantly depending on local conditions? The answer has implications not just for planetary science, but for astrobiology, as the conditions for life may depend on specific planetary and chemical environments. If those environments are rare, life may be rare. If they are common, life may be common. Interstellar objects are one line of evidence in this grand inquiry. The philosophical dimension of studying 3I Atlas and its interstellar cousins touches on questions of cosmic purpose and meaning. Throughout history, humans have sought to understand their place in the universe, and the progression of astronomical knowledge has repeatedly revised that understanding. The Copernican revolution displaced Earth from the center of the cosmos, making it one planet among many. The discovery of the vast scale of the universe and the countless galaxies beyond our own further diminished our apparent significance. Yet, paradoxically, each of these discoveries has also been empowering, expanding our knowledge, and revealing the universe to be more wondrous and complex than previously imagined. The potential discovery of extraterrestrial intelligence or technology would be the next step in this progression, definitively answering that we are not alone, while simultaneously raising new questions about the nature and fate of technological civilizations. It would be both humbling and inspiring, confirming that intelligence is not unique to Earth while challenging us to consider what messages or legacies we wish to leave for future discoverers. Even if 3I Atlas proves to be entirely natural, its study contributes to this broader quest for understanding, revealing the diversity and complexity of the cosmos and our growing ability to comprehend it. The technical achievements represented by the detection and study of interstellar objects are themselves remarkable. A century ago, such objects were purely hypothetical, their existence inferred from theoretical considerations but impossible to observe. The development of sensitive telescopes, digital detectors, automated survey systems, and sophisticated data analysis algorithms has made their detection routine, or at least possible. The improvement in observational capabilities continues, with each new generation of instruments pushing the boundaries of what can be detected and measured. The James Webb Space Telescope, while primarily designed for studying distant galaxies and exoplanets, could potentially be used to observe interstellar objects if they are bright enough and positioned favorably. Its infrared sensitivity would be particularly valuable for studying dust properties and detecting complex organic molecules through spectroscopy. The next generation of ground-based extremely large telescopes, with apertures of 30 to 40 meters, will have even greater light-gathering power and resolution, enabling detailed studies of fainter and more distant objects. These investments in astronomical infrastructure are motivated by a broad range of scientific questions, from the nature of dark energy to the formation of stars and planets, but they also enable unexpected discoveries like interstellar objects. The synergy between planned science programs and serendipitous discoveries is a hallmark of astronomy, where instruments built for one purpose often yield breakthroughs in unrelated areas. The story of 3I Atlas, when placed in the context of these broader developments, is a story of human ingenuity and curiosity, our drive to explore and understand the universe, despite the vast distances and challenges involved. The transformation of the anti-tail into a tail, documented just hours ago, will be analyzed in detail in the coming days and weeks. Researchers will measure the brightness distribution, the spectral properties, and the temporal evolution, comparing these observations to models of dust dynamics and gas emission. The results will be presented at conferences, published in journals, and incorporated into the growing body of knowledge about interstellar objects. Future textbooks on cometary science and interstellar astronomy will include 3I Atlas as a case study, discussed alongside Oumuamua and Borisov as early examples of a new class of objects. Students will study its anomalous properties, debate the interpretations, and perhaps develop new theories that better explain the observations. This is how scientific knowledge progresses, building on the work of previous generations and extending it in new directions. The current observers of 3I Atlas are contributing to this long-term project, adding their data points to the accumulating evidence. The question of whether 3I Atlas is natural or artificial will likely remain contentious until significantly more data is available, possibly from future interstellar objects or from theoretical advances that better explain unusual compositions. In the meantime, both interpretations coexist in the scientific literature, with proponents of each citing different lines of evidence and emphasizing different aspects of the data. This plurality of perspectives is healthy, preventing premature closure on the question and ensuring that alternative hypotheses remain under consideration. History shows that scientific consensus can be wrong, that majority opinion is not always correct, and that minority views sometimes prove prescient. The key is maintaining rigorous standards of evidence while remaining open to revising conclusions when warranted. For 3I Atlas, the evidence is still being gathered, the analysis is ongoing, and the final verdict is not yet in. What is certain is that the object has captured the attention of astronomers worldwide, generated substantial public interest, and contributed valuable data to the young field of interstellar object studies. Its passage through our solar system, however brief, has left a mark on our scientific understanding and our cultural conversation about humanity's place in the cosmos. As the object fades from view in the coming months, it will not be forgotten, but will remain a subject of study and debate, its mysteries continuing to inspire research and speculation. The perihelion passage on October 29 is the climax of this particular story, the moment of maximum drama and transformation when all eyes are turned toward the sun, waiting to see what emerges from the glare. The convergence of scientific disciplines required to fully understand 3I Atlas demonstrates the interconnected nature of modern astronomy. Spectroscopists analyze the light to determine composition. Dynamicists calculate trajectories and predict future positions. Theorists build models of internal structure and thermal evolution. Observational astronomers coordinate telescope time and collect data. And data scientists develop algorithms to process and interpret the massive data sets. Each specialty contributes essential expertise, and no single researcher or team possesses all the necessary skills. Collaboration is not optional but mandatory, facilitated by international agreements, shared databases, and professional networks that span the globe. The coordination required to observe a rapidly moving, fading object like 3I Atlas tests these collaborative structures, revealing both their strengths and weaknesses. When the system works well, data flows smoothly between observers and analysts. Preliminary results are shared promptly, and the community converges on robust conclusions. When communication breaks down or data access is restricted, progress slows and frustration mounts, as evidenced by Dr. Loeb's complaints about transparency. The ideal of open science, where all publicly funded data is rapidly and freely available, remains aspirational in practice, constrained by technical limitations, institutional policies, and human factors. The push toward greater openness continues, driven by recognition that science advances faster when information flows freely and when independent researchers can verify and extend each other's work. The allocation of telescope time represents another dimension of the infrastructure supporting interstellar object studies. Major observatories receive far more requests for observing time than they can accommodate, and time allocation committees must prioritize among competing proposals. Routine observing programs, planned months or years in advance, must sometimes be interrupted to accommodate target of opportunity observations of transient phenomena like interstellar objects. This flexibility is built into modern observatory operations, with mechanisms for rapid proposal submission and expedited review when time-critical opportunities arise. The discovery of 3I Atlas triggered such target of opportunity proposals at observatories worldwide, and many were approved, allocating precious telescope time to this unprecedented visitor. The scientific justification for such allocations is clear. The opportunity to study an interstellar object is rare and fleeting, and the potential scientific return is high. However, the disruption to scheduled programs is not trivial, and some researchers whose observations are postponed may feel aggrieved. Balancing these competing interests requires judgment and flexibility, guided by assessments of scientific priority and feasibility. The success of the 3I Atlas observing campaign reflects the astronomical community's recognition of the object's importance and willingness to adapt plans to accommodate unexpected discoveries. The economic dimension of studying interstellar objects is substantial, but often invisible to the public. Telescope construction and operation, spacecraft missions, data storage and analysis infrastructure, and researcher salaries all require significant funding, typically provided by government agencies, universities, and international partnerships. The costs are justified by the scientific and educational benefits, the technological spin-offs, and the cultural value of expanding human knowledge. Public support for space science depends on effective communication of results and their significance, making science outreach and education essential components of research programs. The media coverage of 3I Atlas, while sometimes sensationalized, serves the valuable function of engaging public interest and demonstrating the relevance of astronomical research. When taxpayers understand that their investment is producing new knowledge about the universe and potentially addressing fundamental questions about life beyond Earth, support for continued funding is more likely. Scientists have a responsibility to communicate their work clearly and accurately, avoiding both excessive caution that makes results seem dull and excessive hype that raises unrealistic expectations. The challenge is striking the right balance, presenting results with appropriate nuance while still conveying their excitement and significance. Dr. Loeb's high-profile advocacy for the artificial origin hypothesis, whatever its scientific merits, has certainly succeeded in raising public awareness of interstellar objects and generating interest in the search for extraterrestrial technology. Whether this attention ultimately benefits the field or creates unrealistic expectations that lead to disappointment remains to be seen. The cultural impact of discovering definitive evidence of extraterrestrial technology would be profound and far-reaching, extending well beyond science into philosophy, religion, politics, and every aspect of human society. The realization that we are not alone, that other intelligences exist or have existed in the universe, would reshape our understanding of humanity's significance and destiny. Different cultures and belief systems would respond differently, some finding confirmation of long-held beliefs about cosmic pluralism, others experiencing existential crisis as anthropocentric worldviews are challenged. The societal preparation for such a discovery is minimal, with little systematic effort to consider the implications or plan responses. The scientific community has developed protocols for announcing the detection of extraterrestrial intelligence, emphasizing the need for rigorous verification before public announcement and international coordination in crafting the message. However, these protocols assume a signal detection, not the discovery of an artifact, and may not be adequate for the different challenges posed by a physical object. The ambiguity surrounding objects, like 3-Eye Atlas, where the evidence is suggestive but not definitive, creates a gray zone where different groups can reach different conclusions, potentially leading to confusion and controversy. Clear communication about the level of certainty and the nature of the evidence is essential to avoid misunderstandings. The distinction between "we have detected something anomalous that requires further study" and "we have confirmed evidence of alien technology" is crucial, yet this distinction is often lost in media coverage and public discourse. Scientists must be careful in their language, avoiding overstatements while still conveying the genuine excitement and significance of their findings. The interdisciplinary nature of the questions raised by 3-Eye Atlas extends beyond science into history and archaeology. If artificial interstellar objects exist, they represent a form of archaeology on a cosmic scale, the study of artifacts from civilizations distant in both space and possibly time. The methods of terrestrial archaeology, inferring cultural and technological information from physical remains, could be adapted to the study of extraterrestrial artifacts, though the challenges would be immense, given our inability to excavate or closely examine such objects. The field of space archaeology, currently focused on preserving and studying human artifacts in space like discarded satellites and lunar landing sites, could expand to include non-human artifacts if any are confirmed. The expertise of archaeologists in interpreting ambiguous evidence, dealing with incomplete information, and reconstructing past technologies and behaviors could prove valuable in analyzing interstellar objects with possible artificial origins. The collaboration between astronomers and archaeologists is not yet established, but could emerge if the evidence for artificial objects strengthens. The preservation of 3-Eye Atlas itself, or at least the data about it, becomes a form of archiving for future study, ensuring that this brief encounter is documented for posterity. The ephemeral nature of the observations, the brief window during which the object was visible and the data was collected, makes preservation especially important. Digital data, unlike physical artifacts, can be perfectly replicated and distributed, but it requires active curation and maintenance to remain accessible as storage technologies and file formats evolve. The astronomical community has developed standards and repositories for preserving observational data, ensuring its long-term availability to researchers. The data from 3-Eye Atlas will be archived in these repositories, tagged with appropriate metadata, and made available to future researchers who may have new questions or analytical techniques that current researchers have not considered. This forward-looking approach treats each observation as a contribution not just to immediate research questions, but to a permanent scientific record that will be consulted for generations. The educational impact of 3-Eye Atlas extends from professional research to public engagement and classroom learning. The object provides a concrete example for teaching about orbital mechanics, spectroscopy, cometary science, and the scientific method. Students can examine real data, follow the scientific debate, and see how astronomers work to answer open questions. The uncertainties and controversies surrounding the object make it especially valuable pedagogically, illustrating that science is not a collection of settled facts, but an ongoing process of inquiry, where disagreement and revision are normal. Teachers can use 3-Eye Atlas to discuss the nature of evidence, the difference between speculation and proof, and the importance of maintaining multiple working hypotheses when data is incomplete. The object also serves to inspire the next generation of scientists, demonstrating that major discoveries are still possible and that fundamental questions about the universe remain unanswered. Young people who follow the story of 3-Eye Atlas may be motivated to pursue careers in astronomy, physics, or related fields, continuing the tradition of exploration and discovery. The long-term impact of this educational and inspirational function may ultimately be more significant than the immediate scientific results, as today's students become tomorrow's researchers and continue the investigation of interstellar objects and the search for life beyond Earth. The concept of time itself takes on special meaning in the context of interstellar objects. The light we observe from 3I Atlas left its surface minutes or hours ago, depending on its distance from Earth, meaning we are seeing the object as it was in the recent past, not as it is at this exact moment. For distant galaxies, this light travel time effect means we observe objects as they were millions or billions of years ago, providing a view of cosmic history. For nearby interstellar objects, the delay is minimal, but it still represents a fundamental limitation. We can never observe the present, only the past. The object's history extends back millions or billions of years to its formation in another stellar system, a past we can only infer from its current properties. Its future, after leaving our solar system, is equally inaccessible to direct observation, knowable only through calculation and extrapolation. We exist in a narrow slice of the object's timeline, the brief period when its trajectory intersected our ability to observe it, and from this slice, we must reconstruct both past and future. This temporal perspective is humbling, reminding us of the vast scales of cosmic time and the fleeting nature of our observations. The legacy of 3I Atlas will ultimately be measured not by whether it is confirmed as natural or artificial, but by how it advances our understanding and capabilities. If it is natural, it expands our knowledge of cometary diversity and the range of planetary formation environments across the galaxy, providing constraints on chemical and physical processes that operate in other stellar systems. If it is artificial, it represents the most profound discovery in human history, proof that we are not alone, and that technology can traverse the interstellar void. Either outcome is scientifically valuable, and the process of investigation itself advances multiple fields simultaneously. The techniques developed for studying 3I Atlas, the collaborative networks established, the observational strategies refined, all will be applied to future interstellar objects, making each subsequent detection easier and more productive. The accumulation of knowledge is incremental, building case by case, and 3I Atlas is an essential early case study in this emerging field. The comparison to historical scientific controversies is instructive for understanding the current debate. The nature of meteorites was debated for decades before overwhelming evidence forced scientific consensus that rocks could indeed fall from the sky. The existence of continental drift was controversial until the mechanism of plate tectonics was discovered and supporting evidence accumulated. The reality of black holes, once considered mathematical curiosities, became undeniable as observational evidence mounted. In each case, initial skepticism was eventually overcome by the weight of data, but the process took time, required multiple lines of evidence, and involved vigorous debate. The case of 3I Atlas is still in the early stages of this process, with limited data and competing interpretations. The resolution may take years or decades, requiring observations of many additional interstellar objects and advances in theoretical understanding. Patience and continued vigilance are required, maintaining both appropriate skepticism of extraordinary claims and openness to revising conclusions as evidence accumulates. The scientific community's current approach, treating the artificial origin hypothesis as a possibility worth investigating while maintaining that natural explanations are more probable, represents a balanced position that serves the goal of truth-seeking. The role of amateur astronomers in discovering and monitoring interstellar objects should not be overlooked. While the initial detections of Oumuamua, Borisov, and 3I Atlas were made by professional survey telescopes, amateur astronomers with sophisticated equipment have contributed follow-up observations, particularly photometry and astrometry. The democratization of astronomical technology, with high-quality CCD cameras and telescopes available at consumer prices, has created a large community of skilled observers who can contribute to scientific research. Coordination between professionals and amateurs, facilitated by online platforms and citizen science projects, multiplies the observing capacity available for studying transient phenomena. Some future interstellar object might even be discovered first by an amateur, continuing a proud tradition in astronomy where amateurs have made significant contributions. The involvement of the broader community in observing and studying these objects fosters public engagement with science and demonstrates that meaningful participation is possible even without professional credentials or institutional affiliation. The question of nomenclature, how we name and classify interstellar objects, reflects deeper questions about their nature and origins. The designation 3I indicates the third confirmed interstellar object, with the I standing for interstellar, and Atlas comes from the survey that discovered it. This naming convention treats interstellar objects as a distinct category, separate from asteroids and comets, acknowledging their special status as visitors from beyond our solar system. As more are discovered, subcategories may emerge, distinguishing between comet-like and asteroid-like interstellar objects, or potentially between natural and artificial, if any are confirmed. The taxonomy of interstellar objects is still being developed, and 3I Atlas contributes to this process by exemplifying the challenges of classification when objects exhibit properties that span multiple categories. Is it a comet because it has a coma and tail, or something else because of its anomalous composition? The answer may depend on which characteristics are considered most fundamental, and different researchers may legitimately disagree. Taxonomy in astronomy, as in biology, is partly conventional, reflecting human choices about which similarities and differences are most important for classification. The goal is to create categories that are scientifically useful, grouping objects with similar properties and origins, but perfect classification may be impossible when nature produces objects with intermediate or unique characteristics. The ethical dimensions of searching for and potentially discovering extraterrestrial intelligence or technology deserve consideration. If we were to detect an active artificial object, perhaps one transmitting signals or exhibiting behavior inconsistent with natural processes, what responsibilities would we have? Should we attempt to communicate? And if so, what should we say? Should we broadcast our existence and location, or maintain silence to avoid potential risks? These questions have been debated in the SETI community for decades, with no consensus on answers. Some argue that active messaging to extraterrestrial intelligences is reckless, potentially exposing humanity to hostile civilizations, while others contend that any civilization capable of interstellar travel or communication would have already detected our presence through our inadvertent electromagnetic emissions. The case of a derelict artifact like 3I Atlas, if it were confirmed as artificial, presents a different set of questions. There would be no communication, no immediate threat or opportunity, just the knowledge that someone else was or is out there. The psychological and cultural impact would still be profound, but the ethical quandaries of active engagement would not arise. The discovery would nonetheless raise questions about our own trajectory as a species. Will we eventually send our own artifacts into interstellar space? And what messages or legacies should they carry? The Voyager spacecraft, launched in the 1,970 seconds and now beyond the heliopause in interstellar space, carry golden records with sounds and images of Earth, intended as messages to any future finders. These pioneering artifacts represent humanity's first contributions to the population of interstellar objects, and in billions of years they may encounter other stellar systems, becoming foreign visitors much like 3I Atlas is to us. The symmetry is poetic. We study objects from other stars while sending our own objects to drift among the stars, participants in a slow, patient exchange that operates on timescales vastly longer than human civilizations. The technological challenge of intercepting and studying an interstellar object up close is formidable but not insurmountable. Several mission concepts have been proposed, ranging from fast flyby spacecraft that would gather data during a brief encounter to more ambitious rendezvous missions that would match the object's velocity and conduct extended observations. The energy requirements are substantial because interstellar objects approach with velocities typically exceeding 20 kilometers per second relative to the Sun, faster than any spacecraft humans have built to date. Reaching such velocities would require either enormous rockets, gravity assists from multiple planets, or advanced propulsion technologies like solar sails or nuclear electric propulsion. The mission design would also need to account for the short warning time between detection and optimal intercept opportunity, possibly requiring spacecraft to be prepositioned or launched very rapidly after discovery. Despite these challenges, missions are technically feasible with current or near-future technology, and the scientific return would justify the investment. A close-up image of an interstellar object's nucleus, spectroscopic analysis of its surface composition, or measurements of its internal structure would provide data orders of magnitude more valuable than remote observations. If 3I Atlas or a similar object were confirmed to have unusual properties suggesting possible artificial origin, the case for a dedicated mission would become overwhelming, potentially galvanizing international cooperation and funding on the scale of the Apollo program. The prospect of humanity's first direct encounter with extraterrestrial technology would be irresistible, transcending national boundaries and uniting our species in a common endeavor. The September 29 date associated with the Claude Sonnet model designation in the system context is unrelated to the October 22 current date or the October 29 perihelion date of 3I Atlas, serving only as a model identifier. The actual timeline of 3I Atlas observation spans months, from its discovery earlier this year through the current intensive monitoring as it approaches perihelion. The coordination of this observational campaign across multiple observatories and research groups represents a significant logistical achievement, managed through informal communication networks, email lists, and coordination meetings, where strategies are discussed and observations are planned. The rapid dissemination of new results through preprint servers and blog posts, as exemplified by Dr. Loeb's announcement of the tail transformation, allows researchers to stay current with the latest findings and adjust their own observational or theoretical work accordingly. This fast-paced collaborative approach is characteristic of modern time-domain astronomy, where transient phenomena must be studied opportunistically and coordination is essential for maximizing scientific return. The success of this model for 3I Atlas bodes well for future interstellar object campaigns, demonstrating that the global astronomical community can respond effectively to unexpected discoveries and work together despite geographical, institutional, and sometimes personal differences. The ultimate goal of studying interstellar objects transcends the specifics of any single object and addresses fundamental questions about the nature and evolution of the universe. How common are planetary systems, and how diverse are their compositions and architectures? What fraction of stars eject material into interstellar space? And what are the mechanisms of ejection? How do interstellar objects evolve during their long journeys through the galaxy? And what can they tell us about the interstellar medium? Are there technological civilizations elsewhere in the galaxy? And if so, what artifacts might they have created? These questions have motivated astronomical research for generations, and interstellar objects provide a new avenue for addressing them. Each detection adds data points, constraining models, and testing hypotheses, gradually narrowing the range of plausible answers. The work is painstaking and incremental, rarely producing dramatic breakthroughs, but steadily advancing understanding through the accumulation of evidence. 3I Atlas is one small piece of this vast puzzle, valuable not in isolation, but as part of a growing dataset that will eventually encompass hundreds or thousands of interstellar objects, each contributing its unique perspective on the diversity and history of the galaxy. The vision for the future of interstellar object studies is ambitious. A permanent monitoring system capable of detecting objects years before they reach the inner solar system, providing adequate time for detailed observational campaigns and possibly spacecraft missions. Spectroscopic surveys capable of determining composition for large samples, enabling statistical studies of population characteristics, theoretical frameworks capable of explaining the observed diversity within natural planetary formation paradigms, and protocols for identifying genuinely anomalous objects that might warrant alternative explanations, including technological origin. This vision requires sustained investment in astronomical infrastructure, continued support for basic research, international cooperation, and public engagement to maintain funding and interest. The progress toward this vision has been rapid over the past decade, accelerating with each new detection, and the outlook for the coming decades is optimistic. Thank you for being with us. Please subscribe and leave a like.